In this video, we're going to cover section 5.3, solving trigonometric equations, still part of unit 5, and hopefully it's not too long. We're going to try to make up for the past two videos, okay? So let's go right into it. Example number 1, we're going to solve, let me just focus this a little bit, it's a little blurry. So we're going to solve sine of x minus the square root of 2 is equal to negative sine of x, okay? So how are we going to do that? Well, I know that when I'm solving, I typically want to set things equal to whatever I'm looking for, right? So we're trying to find x, which means we need to isolate sine of x first. So I'm going to start by moving over all of my sine x's to the same side. And typically I want to keep them, positive just to make it a little bit easier on me. And that's going to give me a 0 on this side. And we get sine x plus sine x is 2 of them. Okay, bring down everything else like so. And I'm going to go ahead and isolate my trig function here. So I'm going to move over my plus square root of 2, which gives me 2 sine of x is equal to the square root of 2. We divide both sides by 2. And so sine of x is equal to the square root of 2 over 2. Now, this is the first part. So when you're solving for trig equations, typically you want to isolate the trig function, so sine, cosine, tangent, whatever it is, and then you want to try to figure out at what angle is this function equal to whatever output you get over here. Okay, so where is sine of x equal to square root of 2 over 2? Okay, well, I know from my little foldable and just from, what I know, that square root of 2 happens here in kind of like these angles here, these pi-4 angles or 45 degrees. And since I want it to be positive, sine of x has to be positive. I'm looking for where y is positive. So we're looking at this top part up here, because up here we have our y value, square root of 2 over 2. Square root of 2 over 2 is positive, and that's what we want. So it looks like we have two places where this happens, pi-4, and this would be 3 pi-4, right? Because 1, 2, 3, so 3 pi-4. So let's go ahead and write that out here. We would have x equals, okay, pi over 4 plus 2n pi. You're asking me, what is that? And we've seen it already, but basically if I were to go around the circle and land on that same spot, so like a coterminal angle, it would also be an answer, right? So basically any revolution of 2 pi would land back on this pi over 4. So that's going to be one of our answers, and the other one is going to be the other one that we saw, x equals 3 pi-4 plus 2n pi. And that is it for this first one. Okay, next we have example 2, solve cotangent of x times cosine square x equal to 2 cotangent of x. This one I went ahead and just solved again, kind of to save on the time here, and so we're going to go through each step. The first thing you want to do is, for this solution to be found, is move everything over to one side for this problem, because you can kind of see that we have some same items here that we can probably combine, okay, and maybe factor at some point. So we're going to move this 2 cotangent x over to the other side, which makes it negative. So it's kind of like subtracting from both sides, okay? So we're left with this. And then, like I mentioned, we can probably factor something. So let's try factoring. I noticed that both of these terms have a cotangent. So there's a cotangent here and a cotangent there of x. So I'm going to take that out, and I'm left with cosine square x minus 2. Once we're left with kind of like these two terms, you're going to set each of those equal to 0. So set equal to 0 like so. And we're going to kind of try to hide some of this first. So we have cotangent of x is equal to 0, and then all of this is equal to 0. Okay, let's look at this one first because I kind of worked it out this way. We have that if I move my 2 over, I get equal to positive 2. So cosine square x equals positive 2. And then I'm going to go ahead and square root both sides. So right here, that didn't show that. I'm going to square root both sides. And that gives me cosine of x is equal to the square root of 2. Okay. So we'll come back to that in just a bit. For cotangent of x, that one's a little bit easier because it's already isolated. We already have our function equal to something. So all I got to say is where does that happen? Okay, and I kind of put here, where does this happen? Well, this happens at pi halves because if you remember, and we can draw the circle here if you'd like, or you can look at your foldable if you want. But here's my circle, and I know that at these points here, okay, this is 0, 0, 1, and this is 0, negative 1. This is at pi halves, and this is at 3 pi halves. Okay, so we're thinking about cotangent. Okay, so here at 0, 1, you can see that if we divide x by y, we get 0. 0 divided by 1 is 0. Now, it does happen down here also, but one thing to remember is that the period of tangent and cotangent is actually just from 0 to pi. It's a period of pi. So for this one, we're only going to consider basically everything on the top, okay? And that means that my solution would be pi halves plus n pi. So not 2n pi, just n pi. And we'll look at a note about that in just a bit. The other example, I'm sorry, the other solution that we found, you'll notice that I put that this happens nowhere. So let me kind of jump over to cosine now. Remember that cosine has a range between -1 and 1. And that is in your foldable as well. If you look at your graphs, which are tab number 4, okay, we can see that cosine has a range from here to here. So square root of 2 is going to be a little bit bigger than that. It's going to fall somewhere a little bit up here. So because of that, this one has like no solution. So there's no other answer for this one because square root of 2 is outside of the range. So I've notated this like this before. Square root of 2 is not part of -1, 1. Okay, so same thing. And I did kind of put a note here that you can confirm your solutions by graphing. If you wanted to do this graphically, which is fine, but you still have to show the work. It would just be to confirm. Remember, you still have to show your work. You would be looking for the x-intercepts. So I'm not going to show that here, but basically what you would do is you would just kind of graph this, look at the graph, and then it'll show you where it's crossing the x-axis. And yeah, that's it. Okay, so let's go ahead and move on to the next one. The next one's going to be the longest set of notes. It shouldn't take too long, but let's go ahead and get through it. Okay, so before we do that, example 3, we do have a note here that I kind of mentioned. Sine and cosine are going to have solutions of the form x equals some number and then plus 2n pi if we're looking for a general solution. I should probably put that here. This is for general solutions because sometimes they will ask you in a specific range only, like you're going to see in this one. So if they say just, what's the solution and there's no interval, then this is the form you want to use. If you're looking at tangent, then we're going to be looking at x equals the number plus n pi. And this is all because of the period, okay? So let's go ahead and look at our next example. Find all the solutions of sine of x plus 1 equals cosine of x in the interval 0 to pi. Notice that 2 pi is not included, so if we do have an answer at 0, that we get x equals 0, we're not going to include 2 pi for that, okay? Because technically it's the same position. And I did have a note here, we're going to be squaring and converting to a quadratic because that's going to help us figure this one out. So we're going to square everything. So let's do that. Let me kind of rewrite this here. We're going to have sine of x plus 1 equals cosine of x, and we'll talk about why I divided this in 2 in just a bit. And I'm going to square both sides. Remember, as long as you do it to both sides, it's kind of okay. We mentioned in an earlier video that you don't want to be changing things if we're proving identities or something of the sort. We're not proving identities here. We are solving. Okay, so it's different. One thing that I do have to note is that if you do something like this, since we're dealing with a quadratic and then square roots and all that, you do have to check your answers because chances are that some of them might not work. So we'll have extraneous solutions, and that's what this side's going to be for. Let's go ahead and do this. So we have on the left side sine of x plus 1 times sine of x plus 1 equals cosine of x squared. Okay, so I just kind of expanded this into 2. We're going to FOIL this. We've already done this a few times in class, whether it's on a math lab or, just different examples, but it's just FOIL, okay? So do not overthink it. Sine x times sine x is sine squared x. Then we have the outer term, so we're going to have plus 1 sine x, or, just sine x. The inside, so another sine x. And then the last, 1 times 1. So plus 1, all equal to cosine squared x. Okay, let's combine these two. So we have sine square x plus 2 sine of x plus 1 is equal to cosine squared of x. Now that I have kind of something going on here, we're going to move the cosine square over. So I would subtract from both sides. And that gives me sine squared x minus cosine square x plus 2 sine of x plus 1 is equal to 0. Okay, so we have this like really big, not that long, but it's a little bit longer to work with now. I have a lot of sines, so I'm going to change this one to a sine by using an identity. So I'm going to change cosine square x to 1 minus sine square x. So let me kind of move this out because I'm kind of running out of room here. So sine of x minus, I'm going to put this in parentheses, the part that I'm changing here. And it's not so much that I'm changing it, I'm just using an identity, which is part of your foldable, okay, to replace it with something that I can probably work with. Okay, I'm just kind of bringing everything else down. Let's distribute that negative. So we have sine square of x minus 1 plus sine square of x, because negative times a negative is a positive. Bring everything else down. Okay, and then we're going to combine like terms. So I have sine square x, which is 2 sine squared x's plus 2 sine of x, like this one. And then we have negative 1 and 1 is 0, so this is just equal to 0. Okay, we're kind of getting there. You can see that we can maybe factor something here. So let's try that. Let's factor out a 2 sine of x. If I take out the 2's and I take out a sine, I'm left with, well, one of the signs there, right? It's like sine, it's like kind of like x squared. You have 1 x left plus 1 because I factored out this entire thing. And now you can see this kind of looks like one of the ones we just did before, where you can set each of these equal to 0 and solve. So that is what we're going to do. I'm trying to get this to not move around so much. So this would be 2 sine of x is equal to 0. This one would be sine of x plus 1 is equal to 0. The first one, you can kind of tell what it's going to be, because if you divide both sides by 2, we get sine of x is equal to 0. Okay, this one you have to do a little bit of work. So minus 1, so sine of x is equal to negative 1. And we're kind of sort of like a little over halfway done. Okay, so now that you have the trig function isolated, you want to identify where this happens. So where does sine equal to 0? Where is the y value equal to 0? If you don't know, look at your little booklet here. You can probably find it on the first one. So where is y equal to 0? Well, it looks like I have a y equal to 0 here at pi and at 0. Remember, we're not going to include 2 pi, so this is also 0. So I have one at 0 and pi. So x is going to be equal to 0 and pi. So far, remember, we are going to have to check these. That's possible answers that we have here. We'll kind of just underline them. Where is sine of x equal to negative 1? Okay, so same thing. Look at your foldables, see where you have a negative 1. Here we go. The y is equal to negative 1 right here at 3 pi halves. So for this one, we have x is equal to 3 pi over 2. And again, these are tentative because we still have to check them. Since we're looking for the solutions on an interval, as it's set up here at the top, we don't put that plus 2 and pi. Okay, we're going to go ahead and check these now. So that is what the other column here is for, right here. Okay, we're going to check for extraneous solutions. I can never spell that word. It might have two N's, I'm not sure. But check for extraneous solutions. Okay, so we do that by taking each x. So we're going to start with x equals 0 and plugging it into the original equation. So the original did not have the squares. Okay, so remember, this is the original one up here, this one. So let's see. That would be sine of 0 plus 1 equals cosine of 0. Oh, I don't know why I put that's a 0, not a theta, that's a 0. Okay, again, not a theta, that's a 0. So sine of 0 is, let's see, we can look at our foldable. At 0 degrees, the y value is 0. So we have 0 plus 1 equals, at 0 degrees, cosine is 1. So we have 1 equals 1. So this one is a solution, for sure. We're going to try the next one. I believe it was x equals pi. Okay, same thing. So we're going to plug in sine of pi plus 1 equals cosine of pi. Let's look at pi. So pi is over here. For sine of pi, I'm looking at the y value, so it's 0. So we have 0 plus 1 equals, cosine of pi is the x value at pi, so it's negative 1. So in this one, we actually have that 1 is equal to negative 1, which is not true, which means that this one is not going to be a solution. This one's going to be one of those extraneous, I think it has double ends, not sure. That's going to be an extraneous solution, okay? Just kind of writing it lightly because we want the ones that are real. Okay, so the last one I'm going to check is x equals 3 pi halves. Let me move this down a little bit. 3 pi halves. And same thing, so we're going to plug it in. Sine of 3 pi halves plus 1 equals cosine of 3 pi halves. That's right there, okay? Don't put the division under the cosine. So same thing, we look at 3 pi halves, it's down here. Sine is negative 1 there, so we have negative 1 plus 1, okay? Cosine of 3 pi halves, if I look at that value, my x right there, that's cosine, is going to be 0. Negative 1 plus 1 is 0. So this is also going to be a solution, okay? So in short, or in summary, I should say, our solutions are going to be x equals 0 and x equals 3 pi halves. Why am I putting, I don't know why I keep extending that line, but that's our answer, okay? All right, next one. I think we're almost done. Actually, this might be the last example we're going to do today. Example number 4. And it's not too bad. I have one more after that, but I think I'll do that one in class. So example number 4, we have solving a multi-angle equation. So we've kind of seen multi-angles or multiple angles, I'm sorry. We're going to do this one a little bit different. So I'm going to start by, just kind of isolating the tangent here. Our angle is x over 2, so it's not exactly just x like it usually is. So let's try some stuff here. I'm going to rewrite it so I don't mess with the original problem here. I'm going to start by moving my 2 over, so plus 2 plus 2. Okay, and that's going to give me 2 plus tangent of x over 2 equals 2. Oh, I changed the value, didn't I? Be careful here. I don't think I'll edit this out. I think I'll just leave it because it has been one of those weeks, guys. So the 2 actually goes here in the front. Make sure you make that correction before we mess it up. It's 2 times tangent, okay? But everything else is fine. So we still add 2, we add 2. There's the 2. And then we're going to divide by 2 in this one. That's why I noticed it was wrong. We're going to divide by 2, which gives us tangent of x over 2 is equal to 1. Okay, so we have successfully isolated the tangent, but now we have this weird x over 2. So here's what we're going to do. We're going to find, well, where is tangent equal to 1, first of all? So same thing, if you need to look at your foldable, look at it. Basically, we're looking for where x and y are the same, because remember that tangent is y over x, right, or opposite over adjacent. So that's gonna be this circle right here. We have that these two are the same here, so if you divide them, no matter which order, it's going to give you 1. And we also have it happens down here. But remember that for tangent, we're just looking at from 0 to pi because tangent has a period of pi. So we're just going to look at this value right here, pi over 4. Okay, so that means that this happens x over 2. That's our angle. The angle will happen at pi over 4. But of course, we're trying to solve for x, right? So we'll kind of put this, that's the angle, okay? If we want to find x, well, we have to solve for x, right? So this is kind of your answer, but if we want to get x by itself, we're going to solve for it. So solve for x. So we have x over 2 equals pi over 4. How do you solve that? Well, you can cross multiply. I'm just going to get rid of the 2 by multiplying both sides by 2. And that would give me x is equal to 2 pi over 4, which is the same as pi over 2. So therefore, x is equal to pi halves. And since this one did not ask for a specific range, we're going to say plus n pi. In other words, if I keep going down the graph of tangent, or if I use the unit circle and keep on doing revolutions, it will happen everywhere I have an integer pi from pi halves and on, an integer on. Okay, and I believe, guys, that that is going to be it for this video. Here is the last example. If you want to copy it, we'll probably go over it in class if we have some time. As always, if you have any questions, just let me know.